Hello, guys, welcome back. Today, we'll be discussing a really interesting topic. A student asks me yesterday that, what is the relationship between statistical estimation and testing of hypothesis? Both are a part of statistics, right? So, what is the relationship between statistical estimation and testing of hypothesis? Why there are two different parts of statistics? What are the relationship? What are the outcomes of it? We will discuss it in today's video. So we will discuss this entire topic and idea in three different portions. In the first portion, I will discuss about what are they in brief portions, brief amounts. In the second, we will be discussing about the connection between both of them, the first connection. And in the third, we'll be discussing about the final connections and one important topic that arises out of this too. So let's move ahead one by one. Let's discuss the birth of statistical estimation and testing of hypothesis. So, what's the basic problem? The basic problem is that you have a population. Out of that population, you're taking out a sample, a smaller sample, which now you assume that this sample represents the population, and from this sample, you use methods. So from the sample, you use methods. So from this, you get a sample. This is population. This is sample. From the sample, you try to understand properties about this population. That's the whole goal. Usually, mathematically, so in the previous one of the previous videos, I have discussed about inductive reasoning and deductive reasoning. So, deductive reasoning will only infer about samples from the population, but we are using the inductive reasoning way, that we're using a sample to infer about a population. So, how can we do that? So mathematically we model it by logically model it by x1 x2 xn. So each sample, each element of this population follows a law. Follows a law, a probabilistic law. So when you take out a sample, it's a group, let's say n elements. So each one of them x1, x2, xn. Each one of them is from the population and they follow that law, L. Now, of that law, we don't know the entire population. So we know that it follows some law with some unknown parameters, right? With some unknown parameters. So our goal is to understand those unknown parameters. So why are these two different topics? So that are like, what are the two different topics that arise out of this whole situation? The first is statistical estimation. It asks you that it tries to get an estimate. So using these random variables, it tries to get an estimate as a function of this. They cook all these elements to get a function, which is a function of these elements, which is very close to these unknown parameters. We call these unknown parameters by theta. So which f of this functions of this some function of this data points is called a statistic. We find a statistic. The goal is to find a statistic which is very close to theta. Okay, and we discuss about all these different aspects of good properties, bad properties, good properties of it. And one such important good property is sufficiency, which we will be needing later on. That's why I'm mentioning it here, which tells that that is kind of an estimate which captures the entire information about theta. The most of the most the 100% information about theta captures the entire information about theta. And testing a hypothesis is nothing but with the same thing, with the same data, we are finding when we are asking questions, we are testing two different hypotheses. That it's a bit more than this. It's asking about whether theta follows between like which hypothesis is most likely true based on this data. It's a different question altogether. Both are about the properties of theta. Both are about properties of theta. But this asks the question of like real question that it's asking with theta is this or that. So it's a decision making question. So testing a hypothesis helps you to make decisions, while statistical estimation helps you to understand the parameter unknown parameters. That's it. The testing hypothesis helps you make decisions, while statistical estimations helps you understand the unknown parameter better. Okay. Statistical hypothesis helps you make decision about the unknown parameter. The statistical estimation gives you an idea, a good estimate, a good uh, number, a ballpark number, of the unknown parameter. So there's an intuition which says that if we don't know an estimate about a good estimate about the theta, how can we make a decision making? So this question comes: if we don't know a good estimate about an unknown parameter, how can we make a decision? Let's say a college is taking admission based on admission test. So they're assuming that a good estimate of the students' performance, students' intelligence, or the skills is the result of the score of the admission test. They're using this as a estimate to estimate the students' actual skill level or intelligence level. Okay, so if they don't know this procedure of understanding an estimate or getting an estimate, how will they take the decision of, okay, I will select this decision of admitting the student or not admitting the student? So therefore understand that they must have a relationship, statistical estimation and testing of hypothesis. So we use the data, there is a data, so we use the data to get an estimate about theta hat, which is close to theta, and using that we can make decision, reject or accept or reject decision. Just like the admission test, you can assume that this the admission test is nothing but, so let's say they will only take in the top 10%, something like that. So essentially x1 x2 xn are the true the estimates of the scores of the exam, the scores, and they estimate the true intelligence. Okay, so let's say scores of a single person. Okay, scores of a single person in n questions. So based on that, they make an average. Like they have an MCQ, they have an MSQ, different options. So based on all the option system and scoring system, they get an theta hat. So they assume that this theta hat is actually equivalent or very close, not equivalent, very close mathematically to the actual skill set or intelligence. And then they use this theta hat to reject the candidate, accept the candidate based on certain, certain criterion. So the question is that how to what is a relationship? And you will not see a relationship unless you take the best possible testing of hypothesis scenario. So there's relationship between statistical, like a really good statistical estimate of theta, a good statistical estimate has an intricate relationship, a good hypothesis testing. This is the part of the second part. What is that? So I will just go through it briefly. A good statistical estimate is a theta is entirely the entire information about theta is captured entirely in the sufficient statistic, right? And a good testicle hypothesis is something, let's say you're testing theta, a likelihood ratio test, let's say, or the name and Pearson lemma. So let's say for theta is equal to theta naught versus theta naught equal to theta one greater than theta naught. So for this, what we used likelihood, right? The ratio of likelihoods, L of theta naught by L of theta 1. And we found out that whether if this is, we use this to show that if this is greater than certain value, we if it's less than certain value, we reject. If it's greater than certain value, we do not reject or we accept. We don't say we accept, we do not reject. So therefore, let's not focus on the right hand side. That's a part of the stress testing, a good testing. This is the UMP test, right? So in some sense, a good testing. Also, it's a good estimate because it's a sufficient statistic. Now, the interesting aspect is that if you do L theta naught by L theta 1, this will be f of the. So this is essentially will become a function of a sufficient statistic, a function of the sufficient statistic theta naught, theta hat. You can prove it by the name and factorization theorem. You can factorize L theta naught and L theta 1 in name and factorization theorem, and you can prove that this is nothing but a function of sufficient statistic of theta hat. So therefore, what it's saying that essentially the best test, a good hypothesis test, is actually using a good estimate theta hat, the sufficient statistic estimate of theta hat of theta, and then using that theta hat to make decision making, which is happening underlying the whole system. This is never told. So that's why it's my responsibility to tell you guys about the story, the relationship, how the statistical estimation and the hypothesis testing are related to each other using this. So what you do is that you you rewrite this likelihood in terms of the Neyman factorization theorem, and you will see that two terms gets cancelled. Only the t and theta terms will stay. So that's an exercise for you. Show that it's dependent upon the sufficient statistic theta hat. The t is theta hat, I mean here. So this is the first relationship, that how a good statistical estimate is related to a good hypothesis testing. And in fact, it's like it happens via statistical estimate. That's exactly what we have observed here. We first find a good estimate and then we make a decision making. The good estimate here is sufficiency, and a good acceptance rejection. This testing hypothesis is nothing but a UMP test. So that's a really interesting relationship. And we can use the relationship to do really beautiful things. And essentially, you will see that every testing a hypothesis, normal, usual, basic problems turn out to be in terms of the reaction region, turns out to be in terms of the sufficient statistic. For example, normal, it turns out to be x bar greater than something or less than something. For anything, it turns out to be the reaction region, the reaction criterion turns out to be, as a result, the rejection criteria turns out to be in terms of sufficient statistic. So, for an example, if you remember that x1, x2, xn, if it follows normal mu comma 1, and we want to test, let's say, h naught mu is equal to 0 versus mu greater than equal to 1. So what we did that reject h naught if x bar is really, really large after a certain value, is larger than certain value. That depends upon the level of significance certain value, but understand that x bar is nothing but giving a really good approximate estimation of mu. This is a mu hat. So therefore, whatever the mu hat behaves like, this will transfer to the mu behavior, right? That's the intuition of it. So x bar is nothing but a reflection of mu in the known in a known data set. So therefore, if mu is 1, mu is more than 0, that means it must be reflected in x bar and vice versa. If x bar is more than certain quantity, most probably it's supporting that mu is more towards 1, not towards 0. So this is the basic idea. So x bar is reflecting the behavior of mu and vice versa. Okay. So this is the whole idea. And therefore, a sufficient statistic reflecting the behavior of the parameters. And therefore, the decision making is dependent on the theta hat. Okay. This is really beautiful idea. The next part is nothing but the confidence interval. So what is the confidence interval? It's nothing but it's saying that find an interval, find an interval of a comma b. So x1, x2, xn is a data set of something with the parameter theta, of something with parameter theta. Now, essentially, from this data set, you have to find a A and a B. A and B are understand are functions of the data x1, x2, xn. Are functions of data. So this is statistical estimation and testing hypothesis mixed together. You will see how. Initially, it will seem like a statistical estimation problem, but essentially, it can be derived out of testing a hypothesis. C and B are functions of x1, x2, xn, right? So, for example, let's say if x1, x2, xn follows normal mu comma 1, a good estimate of mu can be x bar, right? A good estimate of mu can be x bar, but we are interested in a region because we may not get pinpoint answer, right? What about we get a region? That's a better estimate, right? So we want to get a good estimate, a good region of of theta, of the parameter theta. So that's the whole problem. The goal is to find an estimate, a good a comma b estimate of theta, like a good estimate or region or interval for theta. But this is the catch. This doesn't mean that theta will always lie here. Let's say we get a to be x bar minus 0.5 and b to be x bar plus 0.5. So therefore we get x bar minus 0.5 to x bar plus 0.5. This is a confidence interval for theta. There's another parameter, confidence interval. There's another parameter, alpha, or certain percentage. It says, or 95%, let's 0.95. It says therefore that x bar minus 0.5 less than theta less than equal to this x bar plus 0.5. इसका probability is 0.95. This is what it means. So essentially, we are trying to find an a comma b where a and b are functions of the data point such that a less than equal to theta less than equal to b. इसका probability is 0.95. But there is another catch again. This is what the definition of a confidence interval means. But this doesn't make sense sometimes. Why? Because theta is not a random variable. Theta is not random. So what makes sense? This does not make sense. So, but what makes sense? If you rewrite this as x bar less than equal to theta plus 0.5 and greater than equal to theta minus 0.5, then this makes sense because here x bar is is a random variable. So this makes sense. But the previous thing does not make sense, right? So what does this mean intuitively? It means that understand for different data set, let's say for another sample, you will get another different xn, a and b, right? So therefore, a and b changes with data. So what does it mean to say that a comma b is a 95% confidence interval? Like what does it mean to say a comma a less than equal to theta less than equal to b for theta? This doesn't make sense. So we converted equivalent to in terms of a less than equal to. Essentially, you can see a less than equal to theta comma this is nothing but it's same as we can show that the data set lies between in a certain set, which is denoted by theta. For example, here the mean lies between certain set. So you can write just set of all x1, x2, xn such that x bar belongs to s theta, where s theta is nothing but this theta minus 0.5 and theta plus 0.5. So therefore, you can simply make it like the probability the xn, x1, x2, xn belongs to certain says theta, right? So, so what does it mean? It means that if you, let's say, if, so therefore, let's say you got that, let's say you got this, that confidence interval for theta is this. Is a 95% confidence interval for theta. I will call it CI. It means that if you repeat the experiment, so understand for different x1, x2, xn, every single time you will get, let's say in the first one you will get 1.3, 2.7. In the second one you will get, let's say 1.9, 3.2. In the third one you will get, let's say 0.5, 4.9. And different sample, different experiment, you will get different outputs, right? So what does it mean that theta lies between this? So it's not fixed, right? So if we take the intersection of all of them, it may be disjoint. So what does it mean? It means that 95% of the time, so if we do this experiment 100 times, on average 95 times theta will be lying between this actual between this between this, and in five times among this 100 times theta will not be lying between this thing. This is counterintuitive, right? But this is exactly what probability means. That exactly this is exactly what probability means, that because x bar is a random variable, this whole thing is changing. So therefore 95 times out of 100 times this will be lying in this region, in one of in each of this region actual theta. We don't know what it is, but it will lie in each of this in one of these regions. But 5 times it will not. And the thing is that we don't know when it will and when it will not. That's the fun. So belongs to the region found. So this is something a very interesting concept, very useful concept that one should know. So this is all about confidence interval. You want to find nothing but an upper bound and lower bound a comma b, which is a function of the data. That's why I'm denoting it right this for theta. Such that probability ax less than equal to theta less than equal to bx is equal to, let's say, 95 or alpha percent 95%, let's say, or whatever, such that this happens. No, the question is that, okay, this sounds to be estimation problem. So we have so many estimates of theta, right? So we have theta has a UMV estimate, we have a sufficient estimate, EMVV sufficient, so many estimates. So which estimate to take? How to find the confidence interval? Such a very good confidence interval. How to find it? So testing a hypothesis gives a really interesting result. And that's really interesting because once you know it, it's done. A good testing, good testing of hypothesis. Let's you take a good testing hypothesis. What does it say? Let's say H naught is saying that theta is equal to theta naught versus H1. Theta naught equal to theta 1, where equal to theta naught. What you're doing? We are assuming that under, so what we are doing, we are finding a test statistic, right? Let's say we have got theta x bar. So what we do? We find out a test statistic t, right? Or we find out what? We find out what, understand very carefully. We find out a rejection region R, which is a subset of the entire data set, entire sample space. Such that in that region, we reject, for whatever data point lies in that region, we reject H naught. Otherwise, else, if this happens, else, do not reject. So let's see an example. Let's take x1, x2, xn follows normal mu comma 1. And we know that Vh naught is mu is equal to 0 versus mu equal to 1. So what is the rejection region? We reject H naught if x bar is greater than c, certain c. So let's say alpha, for alpha, what we do? So we want to find that probability x bar greater than c is rejected given H naught is true, that is mu is equal to 0. This is alpha, right? This is the type 1 error. You have to know these things. And from this we get the C alpha. So therefore, what do we get? We get, using this, we get a rejection region, an acceptance region also. So therefore, we get that if in this region, if the x bar, if it's greater than C alpha, we reject, and here we accept with 95% with alpha minus 1%, and we reject with alpha percent. So we know this given that x bar xi follows 0, right? Also, we can find a good test, right? We know there's a good test for by likelihood ratio test mu is equal to 0 versus mu not equal to 0. For that, you will get that x bar is less than certain quantity C alpha and greater than certain minus C alpha, same quantity. This is non-rejection region. And if outside this rejection region, right? So this is really interesting because if mu is equal to 0, then probability x bar less than c and greater than minus c alpha. This is a non-rejection region. So it's 1 minus probability rejection region. That is, it's 1 minus alpha. So therefore, automatically, see, observe that automatically, and it's for mu is equal to 0. For mu is equal to, there's a theta naught, it'll give minus theta naught. So therefore, observe, for mu is equal to mu naught, let's say, this will give what? Probability minus c alpha less than x bar minus theta or mu naught. less than C alpha is equal to 1 minus alpha. So we get mu naught less than x bar plus C alpha and x bar minus C alpha. It's equal to 1 minus alpha. So that is what the confidence interval is all about. So therefore, like one of the examples, so therefore, you get a confidence interval via testing a hypothesis. And you can get it via likelihood ratio test also. Any test. For any test, you will get a confidence region. But it can be proved that for a good test, you can get a minimum length. Like, understand, if you increase the length, let's say this is a distribution, okay? So x bar is a distribution. So if you increase the length, of course, the probability after a certain time, to increase the length, the probability after a certain time will, of course, be increasing, right? So the goal is to find out the minimum length. A good confidence interval means that the length is also minimum, the length of the interval should be low too. So it can be shown that for good statistical tests, this is minimum, the length is minimum, 2C alpha. So this is the relationship between, so confidence interval is giving a confidence interval, confidence bound for theta, but it does not mean theta will always lie in that. We have already shown that. But what the goal was to show that this finding a confidence region for theta is nothing but estimation problem, finding a behavior of theta, right? Approximate behavior of theta from the data, from the sample data. But we are using this statistical testing a hypothesis to find a confidence interval of theta, and it can be proved that it's good. So this is the beauty of the relationship of statistical estimation and testing hypothesis. Okay, so thank you guys, I hope you enjoyed it. Do share your views in the comment section, guys, and I really loved it. So we discussed 3 points: how the entire uh, the relationship with statistical estimation and testing hypothesis, and then we move ahead to found the first intersection, the first common point, and the whole idea of this um, like sufficiency and finding like good tests are sufficient, contain sufficient statistic in them. And then we moved ahead to find the confidence interval. Okay, the idea of confidence interval and how good tests can give good confidence interval, okay, where the region is low. And also it tells you that what's the meaning of a confidence interval. That's a bonus, what is meant by a confidence interval. That's really interesting. I hope you enjoyed it, guys. So thank you. If you enjoyed it, do share your support by liking and subscribe to our channel. And I will see you in the next video. Stay tuned and stay blessed. Bye bye.